Okay, let's get started here. So project number 2, I think I changed this after class last night. I decided to make it due on Wednesday at noon. So Wednesday, September 26th. Test number 1 will be Tuesday, October 2nd. I actually completed writing the exam yesterday, so we'll spend a little time at the beginning of class discussing the exam, just kind of talking about some of the stuff that we talked about the very first day of class and some other small details just to make sure you understand the format of the test. Are there any questions before we begin? Okay, so let's briefly talk about the exam. We will have a more comprehensive review, or an actual review for the exam, on Thursday, September 27th. So as I mentioned the first day of class, the exam will be computer-based, meaning that you will be able to, or at least partially computer-based, you will be able to use the computers that are at your desk in order to do particular computations for the exam. On each of these computers, again, we have R, TIN, and RStudio. So you can use those 3 software packages. You can have those open. You can also have open a web browser that's pointed at the R help, but and also my corresponding course website. But other than that, that's all you can have open on your computer. So don't be chatting away with some other students in class via the computer. Now, basically, there's going to be a number of problems on the exam. Some will require you to use R, some will not. So it's not every single problem you're going to use R. For the stuff that requires you to use R, well, let's say maybe you need to estimate a regression model. Well, use R, estimate the regression model, and then write your answer on the exam. So I'm still going to give you a paper copy of the exam as you would expect in any other class. But now you write your answer on the exam itself. I guess the first time I did a computer-based exam was actually 6 years ago for this class. I actually had all the students type their stuff in Word. Some students were good at working with equations in Word and some were not, and it just didn't work out well. So that's why I have everyone still write everything down on a piece of paper. So essentially, instead of using, let's say, a calculator on the exam, as you may, let's say, in some other classes, you're using a computer instead. You do not need to write the code that you use to do some kind of computation. You do not need to write that on the exam. You're welcome to do it, but that's going to maybe perhaps take you a lot of time. But you will need to give me some proof showing me how you actually completed your calculations. And we'll discuss that more on September 27th when we discuss the exam in more detail. The exam is closed book, closed note, but you will have access to all my R programs. So everything that's on my R webpage you can use, because I don't want you to have to memorize R code. So let's say that you need to estimate a regression model, and for some reason you don't remember exactly what function we used to do that in the past. Well, you can go to my highschoolcollegegp.R program, bring it up, see that we use the LM function, copy and paste that maybe into your own program that you're going to write, and then make some changes to it and estimate your model. So again, just to emphasize, you will not have access to any of the homework. You will not have access to any of the answer keys for the projects. You will not have access to any of the lecture notes. Only the R programs. Now, let me just make sure that you also understand this. Let's see. I can see what's on your computer screen. So, for example, let's see. We got somebody right now looking at the UNL website. Let's close that out. We had somebody that was looking at Twitter just a few seconds ago, but they have quickly changed what was on their screen. I can see what's on your screen. So don't be looking at a website you shouldn't be looking at during the exam. Okay? So I can see what you're doing. I have been given these kinds of exams now for about 6 years. And every once in a while there's going to be a student who just is not paying attention to what I just said. And if I see you looking at another, like let's say I see you looking at my lecture notes, that's cheating. Okay? So only R, TIN, R Studio, R Help, and also any of my R programs. Those are the only things that you can have open on your computer. Okay.
What about the graphs?
Excuse me?
The graph. We have to like.
Well, that's within R.
But you don't have to pay some way. And then have just to analyze the graph.
Or, okay. Obviously, you can have an R graphics window. That's what I thought you were talking about, open in R or R Studio. But obviously, I cannot have you turn in an actual graph with the exam. What I can have you do is ask you to produce a graph and ask you to interpret it on the exam. Or I guess I could have you sketch out the graph on the exam. But obviously, you cannot copy and paste what's on your computer screen onto your exam that you're turning in. Okay? Now, with the exam, I'm going to obviously pass out a paper copy of it. But what I also will pass out is this formulas and R function handout. And what that just essentially is, looks like this. I don't want you to have to memorize formulas in this class either. So what I've done is just went through the chapters and found what were just important formulas that we had seen. So Chapter 1, Chapter 2, and Chapter 3 formulas will be given to you. Also to help you out in terms of finding the correct R code is I went through all my lecture notes and I've basically written down or typed out particular functions that we've used. So for example, the LM function, and I've given you a brief description of it. So maybe this will help you save time instead of necessarily looking back at one of my old R programs. You can look at this sheet as well to remember, oh yeah, it's the LM function that I need to use to estimate a regression model. And so you can download this handout from the tests and quizzes webpage. I recommend that you do that before the exam so that you can see what information will be given to you. You do not need to bring this handout with you. I will provide you a paper copy of it that's clean. Okay, let's see if there was anything else I needed to discuss. I think that's it. Do you guys have any questions at this time about the exam, about the format? Hold on, okay. The class period. Now, the reason why I give you an exam like this versus maybe what you get in other classes where it's all just on a piece of paper, is because this allows me to assess you in the way that you actually do statistics. You know, you use a computer. So this kind of an exam allows me to assess you in that format. Okay. So, yes?
So which means all points are?
Yes. Well, I'm sorry. When I say R help, I'm talking about the R-based help. So when you type, let's say, help, parentheses, LM, and parentheses, and R, that brings up the help window for the LM function. So, yeah. So don't go to blogs. Don't go to the R listserv archive. I'm talking about help, one way to access the HTML help, and go that way.
Okay, so that's
Yes, that's what I'm talking about for R help. Sorry if that wasn't clear. Any other questions? Okay. So let's take out this section 3.4 to 3.6 document. So one of the things that we're concerned about with a regression model is the assumption of constant error variance. And again, what that just basically means is our epsilons are distributed independent normal 0 sigma squared, where each of your epsilons, each of your error terms have exactly the same variance. And we looked at some ways to make a determination of if that occurs or not. One of the ways was to do a plot like this, where we had y hat here, we had the residuals here, and if we saw a pattern that looked like this amongst your residuals, notice that the variability in the residuals grows as a function of y hat. This suggests that you have non-constant error variance. Another version of the same plot that would help you with that, or would be represent non-constant error variance, is if I had, it's like my pen is out of ink right now for some reason. Let's try this again. Oh. This way? Yep. I'm having to do this with my mouse, so it's not as pretty. Not that it would be pretty anyway. It's not as pretty as it would have been before. But the purpose here is to demonstrate that on the outer edges for y hat, we have smaller variability than what we do in the middle. This is another example of non-constant error variance. Let me close outward here, come back into it, and hopefully I can use my pen again. Sure would be nice. Use it on there. Use it there. And now I can use it again. Good. Okay, so there are actual formal hypothesis tests that help you make the decision of, do you have non-constant error variance? These are not necessarily meant to replace looking at a plot that, like we just saw, rather just to complement these plots and help you make a judgment. So we're going to talk about two different kinds of tests. One's called the Levene's test. And simply here are the hypotheses. HO is constant variance. HA is non-constant variance. So if you reject HO, that means you got a problem with the assumptions of your model for a particular data set. Now, this test is used when, or it's best used when the error variance is consistently increases or decreases as a function of x. So when we have something like what we have in the first plot, or the top plot, that's what this test is designed for in terms of to detect non-constant variance, such as what we have in the top plot. It is not designed to detect non-constant variance as what we see in the bottom plot, though. So it's not perfect. And you'll see why it's designed for more of the top plot situation than the bottom plot situation. One of the nice things is, too, with this particular test is that it doesn't matter if your normality assumption of the epsilons is violated. This test still works. If you remember last time I mentioned to you, you can often have both non-constant error variance and the normality assumption being violated at exactly the same time. So that's why this test can be nice. So here's how here's how you form a test statistic and perform the test. It's a five-step process. First, find the residuals from your model. Okay, no big deal there. So in other words, you're finding what we have been calling our E sub i's for I going in. But now divide the data into two groups using the median of x, and put the the corresponding observations that are in group 1 and, let's say, one group of residuals, and the observations for group 2 have a second group of residuals. So in other words, get my toolbars out. So in other words, we have something that looks like this. Suppose here's X, here's Y. We have, some points here. Those are supposed to be points. And here's our regression model that's supposed to go through the middle of those points. Basically what you're going to do is this. Find the median X value. Let's say it's about here. And divide your data into two groups. The residuals that you get in the first group are going to be denoted by E sub I1. The residuals for the second group are going to be denoted by E sub I2. Okay. Do some more points here to emphasize something coming up. There we go. So that's step 2. Step 3, find the median residual value for both groups. Let's call these medians E tilde. So you got E tilde 1 and E tilde 2. So it's kind of a central location for the medians. Step 4, now find the differences between these residuals and their corresponding group median. Find the absolute value of that difference. Since it's a difference, we're going to call those D's. So, does anyone know basically what this is representing then? What these D's are representing? Or what they help you do? Hopefully I don't have the answer there. Well, how do we find a variance typically? We take the data value minus the mean, and then since we can have positive or negative differences, how about we square it? So essentially we're kind of doing the same thing here, except for now we're working with an absolute value instead. So by looking at these D's now, that allows us to measure the variability in group 1, and what we're going to do is compare that variability to the variability that's in group 2, simply by looking at these differences. So for example, go back to this plot. So we're going to find these D's. And let's say that for group 1, we could find a D bar. Just the average of those differences. And for group 2, we could find a D bar as well. What do you think in this particular plot for these D bars? Are they going to be similar to one another, or are they going to be different? A lot different. Similar, because it looks like the variability, these points around the line, are very similar for the two groups. How about instead, we have this situation where now we have all these other residuals. I'll draw some more residuals down here, where now it looks like the residuals that would be in group 2 have a lot more variability. So what's going to happen then to D bar 2? Is it going to stay the same or increase? It's going to increase. D bar 1 is going to be about the same. So how do we compare means? Well, how did you learn in your very first stat class to compare means in a formal manner? Do a t-test. Yeah. Do a hypothesis test for the difference of two means. And so in step 5 then, we simply use a standard 2-sample t-test now using these D's. So this is a formula you should all be familiar with. This uses a pooled variance in the end in terms of how it's calculated. But now we're just working with the D's. And this test statistic has an approximate t-distribution with n minus 2 degrees of freedom. So how would you determine if you reject HO? You compare this value to what? A t-distribution critical value. Do you think this is going to be a one-tail or two-tail test? 2. You know, because d bar 1 could be greater than d bar 2. D bar 2 could be greater than d bar 1 to indicate evidence against the null hypothesis. So what we can do is find, let's say, the 1 minus alpha divided by 2 quantile from a t distribution. And we could then compare, let's say, this is how you would have done it in your first stat class, compare the absolute value of t star to the 1 minus alpha divided by 2 quantile from the t distribution. If this occurs where you have a greater than there, that means reject. Don't reject. And so then, in terms of what we're really interested in, if I reject HO, that says then I have non-constant variance. That's Levine's test. Very simple. So let's take a look at an example of its application. So we're going to work with, again, the high school and college GPA data set. And as we've done before, we estimate our model using the LM function. Now, there's a nice little function that does the test for us. And this function exists in a package called CAR. This is a package that you will need to download yourself to use it. Make a note to myself for a second. CAR stands for Companion to Applied Regression. It's a nice little acronym. CAR package. Hopefully you've also been taking a look at that additional recommended book that I had for this class by Fox and Weisberg, and the book's called Companion to Applied Regression. These are the corresponding functions that are mostly discussed in their book. Now, to use then their function called Levine test, what we need to do is first construct this grouping of our data, which was outlined in step 2. So to do that, one way is to use what's called the if-else function in R. The if-else function works pretty much just like the if function in Excel, if you're familiar with that. And simply we can do this. If-else, I want to test something. I want to test to see if my high school GPA is less than the median high school GPA. So for every observation, I want to do this. And for those observations where the answer is yes, how about we have a result of a value of 1? If the answer is no, a result of a value of 2. I'm going to put this all into an object called a group. Let me actually go over here to R to do this. So those are all my groups. And just to show you in the context of our data, so the median happens to be about 2.33, I believe. So we can see for let's see, let's just find the median to make sure. 2.37. Okay. So we can see here for a high school GPA of 3.04, that observation is assigned to group 2. High school GPA of 2.35, that's less than a median, so it becomes group 1. Then, to actually run the test, we just say Levine test. There's an object that's simply called y, and that's where we put in our residuals. And then we have an argument called group, and it just so happens we happen to call our grouping object group as well, just because it was simple. And when I run this, this is what I get. Just focus now on that p-value there, 0.7851. So the p-value is large, meaning that there's not sufficient evidence to indicate that there's a problem with our constant error variance assumption. Okay. 2 notes though. Notice there's a warning message there. Did I do something wrong? No, I didn't do something wrong. This warning message comes about with respect to what R was expecting for this group argument. It was basically expecting some kind of categorical variable, like group A versus group B. Now, if you notice that group itself, in terms of our object that we create, is actually numeric. And so R saw that and said, oh, this is a numeric thing. I'm going to transform this to being this categorical variable. And how does it do it? It simply uses a function called factor. And it just simply applies that function factor and transforms it. And you can see it looks just exactly the same, but the way that R now sees this is that there happens to be two levels, two categorical levels. It just so happens they have numerical values called 1 and called 2. Okay? So the warning message means nothing to us, but it's a little bit of information about what this actual warning message means. Second, notice we have something called F value here, and we have something that's PR, standing for probability, greater than the observed value of F, indicating that this is a p-value. Well, remember the relationship between a t distribution and an F distribution. A t random variable, if you are to square it, and suppose that t random variable had a degrees of freedom of, let's say, A, just to be general. Then that's equivalent to an F random variable with degrees of freedom of 1 and as a numerator and A as a denominator. We talked about this back in chapter 2. And so this particular function ends up working with an F distribution versus a T distribution. That's all. P-value will be exactly the same. And so what's the T star value that we had on page 352? Well, all I need to do is take the square root of the test statistic value. It's 0.2767, and actually it ends up being a negative 0.2767, as you will see shortly. Okay, are there any questions? Well, let's actually go through some of the calculations ourselves. Really, we don't need this function. I mean, it makes it more convenient. Well, let's quickly go through the calculations ourselves just to show us that, what R is doing is really not that difficult. So what I want to do is basically go through those 5 steps that I outlined on pages 51 and 52. So we've already found the residuals, simply mod.fit $residuals. Next, what I need to do is find the median by group. So I'm going to create an object called e.tilde, and I'm going to use a function called tapply. What tapply allows me to do is apply the same type of function to multiple segments of my data that I have. So in this case, my data, represented by the x argument, is my residuals. And I want to apply a particular function by group. Just our syntax, use the argument index. So I have 2 group numbers, 1 and 2. And then what function do I want to apply per group? The median. Because I want to find the median residual for those 2 groups. So run that. E.tilde. Here we go. So the median for the first group, or E.1, is negative 0.077. If I want to, I can simply access particular parts of it, as we have done in the past, just by putting the correct indice there. Okay. Next, what I have in this code is I decided to put some information in data.frame to help you see what's going on. So I have data.frame, I put the original data set, I put the residuals, I put the group number, and then I put in the corresponding median residual. And notice how I do that. For whatever's in group, I'm going to pull out the first element or the second element of e.tilde, like I just had shown you. So here's my data.frame, and you can see how group 2 has that corresponding median, and group 1 has that corresponding median as shown here. Next, I'm going to form my Ds. These are my differences. I take the absolute value using the ABS function, take the residual minus the corresponding value for E dot tilde. Notice how I get the right value by using the group argument there. So for example, I'm going to put these D's in my data frame. So we can see that 0.265 minus 0.09 absolute value is 0.0175. Next, finally, I need to do my t-test. Well, there's a function called t.test that does it. We saw this in our introduction to R notes. We did a t-test for one mean. Now we're doing a t-test for difference of two means here. And the way that we can do that is to say formula equal, my data is in D, tilde group. Again, group tells me if it's in group 1 or group 2. I'm going to test for equality of the means, the difference of means to 0. var equal true allows me to do a pooled variance. Alternative equal two-sided test. And here's my test statistic value. Notice if I were to square that, I get that F test statistic value that we saw before, and also the p-value is exactly the same as what we had before as well. So, here's how you do it. Any questions? Okay, let's turn to page 55, please. This is the second test we're going to learn about, called the Boyce-Piggin test. I'll just call it the BP test for short. What differs this test from the Levine's test is that it assumes that you do have a normal distribution for your residuals. So it's less general with respect to that aspect. But it allows you to also find non-constant variance that might be in other forms than what we just saw before. So it allows you to maybe pick up some other stuff. And so what we're going to do is assume that our predictor variable is related to our variance in this manner. So notice how I have a little subscript I on the sigma squared. So I'm allowing I to be potentially different for every single observation. And so log of sigma squared I is equal to gamma 0 plus gamma 1 times xy. So it kind of looks like a regression model. But all this setup allows us to do is think of, our sigma squares coming about in this manner as a function of our predictor variable. Notice that if gamma 1 was equal to 0, x of I disappears, and thus your sigma squares would all be equal to one another. So essentially what we're going to be doing is doing a hypothesis test for gamma 1 is equal to 0 or not. And that tells us, do I have constant error variance or non-constant error variance? So here's our hypotheses. We're going to use this as a test statistic. Don't worry about how this test statistic comes about. But I do need to tell you that make sure you understand the components of it. SSE, sum of squared errors, comes from just a regular old regression model. So using y as a response variable, x as a predictor variable. This SSR star is like an SSR that we've been discussing. The only difference is it comes from now using a new regression model where our residuals from our regular regression model are squared. And we use x as a predictor variable. So in essence, it's kind of like what we see up here. Okay. Now, in a large sample, this test statistic has an approximate chi-squared distribution with 1 degree of freedom. What that basically means then for us, that if this x squared BP is greater than a chi-square random variable, 1 degree of freedom, and we're looking at the 1 minus alpha quantile, if this happens, reject HO, you have non-constant variance. At least if you would take state 801 here, You've already seen what a chi-square distribution is, if by chance you don't know what a chi-square distribution is. This morning, when I was preparing for class, I put together a little introduction to what the chi-square distribution is, and I put it right there if you need it. Okay. So the steps to do this test. Well, get your regular regression model, get your sample model, calculate SSE. Step 2, square your residuals. Use this as a response variable. Fit a new regression model using X as what I have predictor variable, I should say. What I have independent variable there, I should say predictor, to use our terminology. Find SSR, calculate the test statistic, and calculate the p-value from there. Okay, so let's apply this. So with the college and high school GPA data set, there happens to be a function that does the test automatically for us called BP test. It exists in the LM test package, linear model test package. To do the test, there's an argument called formula. You just write it out like you would normally in a LM function. Specify your data, and then you have to add this additional argument, student ties equal false. Without getting into all the details, what student ties equal true means, which is the default, it provides a slightly different version of our test statistic. Student ties equal false gives us the test statistic that we define in the book. So your test statistic in this case ends up being 0.1959. P-value is 0.658. So there's not sufficient evidence against the constant error variance assumption. We don't reject HO. So what does that mean in a practical sense? Seems like doesn't seem to be a problem here. So let's just proceed with our model like we had been. Now let me just remind you, when we were looking at, well, I'll hold off. Let's take a look at a second example where we do have problems with constant error variance. This involves the trees data set that we looked at previously in class. If you remember, we're using the height of trees as a predictive variable, and the response variable is the volume of the trees. Just remember, I can see what's on your screen, and I guess for one student, I am boring them right now, and they're looking at comics, it looks like. Anyway. Let's say that I've already estimated the model, and the results are in mod.fit. So using the same ideas as before, we can use the Levine test function, and we get a p-value of 0.0154, 0.0145, indicating that there is evidence of non-constant variance. Well, does this make sense compared to what we've done before? Well, this was a residual versus y-hat plot that we had seen before, and you can see that looks like we had this funnel-shaped pattern amongst the residuals, meaning that the variability amongst the residuals is growing as a function of y-hat. So this p-value that we're getting, it's kind of small, is basically what we would expect given what we had seen previously. We can also do, oops, the wrong file. We can also do the BP test. Notice we get a very small p-value indicating that there's evidence of non-constant variance. Well, with this trees data set, if you remember, this is where we were looking at the Box-Cox transformation. And we found that a Box-Cox transformation of y to the negative 0.19 power might help solve our problem with non-constant error variance. Well, what happens if we did it, and then re-estimate our model and take a look at the Levine's test and the BP test. So suppose that the results from our using our transformation of our y is in mod.fit2, and we apply Levine's test. Look at that p-value, quite high. Look at the p-value for the BP test, quite high as well, indicating our transformation worked. Great. Well, also, if you remember, we also tried a log transformation. Suppose the results from that log transformations are mod.fit3. And this is what we get. P-values, again, are large. So that's good. And that concludes, then, this set of notes. Yes?
Do either of these tests suggest a way to remedy non-constant variance problems? Or
No. So, you know, that's why it's good to look at the other stuff that we talked about too. Other questions? Okay. Let's move on to the last set of Chapter 3 notes. This is a Section 311. So let's go through the process of all these examinations of our mod that we've been doing. Let's now apply them all at once to the high school and college GPA data set. So in a real-life application, what you want to do is you get your response variable, you get your predictor variable, you collect the data, estimate your model, and then the next step of what you would do in a real-life application is now go through all this Chapter 3 material that we've just discussed to make sure that all your assumptions are satisfied. And to help make your life simpler, and I mentioned this function last time, I've basically written this function called examine.mod.simple, that's in my program, examine.mod.simple.r, that does all the plots, does all the calculations for you. You just need to be able to interpret. Well, one of the things you need to do is be able to interpret then the corresponding results. Now, you still are responsible to understand what's inside the function and how it works. Basically, all I did was I copied and pasted the code that we were using previously for all our little examinations. I put them into this function. So understanding what's inside this function is really not that difficult. I will mention a few things about this function in about 30 seconds. But I do want to mention that on my website, there is a link to a video description of what's inside this function and how to figure out what each component of the function does. I do recommend viewing that if you need help understanding an aspect of R. So this is what the function looks like. Let me just jump over here to 10. There we go. I give some description at the very beginning of it, you know, what the function does. Examine.mod.simple gets a function. The first thing that you need to pass into it is the results from the LM function, what we have been often calling mod.fit. Pass that in as the first argument. And then everything else is set to default values. So for example, do you want a constant test for constant error variance? The default is false. If you want the test, like what we just talked about, make it a true. Let's see. Do you want to find the Box-Cox transformation of lambda, of y? In other words, find that lambda value? Well, by default, it's set to false. If you want to do it, set it equal to true. And, well, what values do you want to look for in terms of the range of lambda? -2, to positive 2. And then there's an argument for x and y. We'll discuss what those mean shortly. Okay. Now, in order to get this function in R, as we discussed last time, you need to basically run this whole function. The quickest way, at least in Tim, is to come up here to the send file icon, and it uses the source function to basically get the function in R. That's all. Real simple. Now, when you look through the function on your own, like I said, I'm not going to talk about all the details here in class. What I've done is I tried to comment what each part of the program does. So if you remember when we ran it in class last time, there was 3 graphics windows that can come up. So I divided everything up by graphic window. And you see familiar code to what we've seen before. Box plot, strip chart. I'm going to do a plot of x versus y. I'm going to do a plot of x, the residuals versus x. And please, take the time, go through the function itself. Here you see some information about Levine in the BP test. And at the end, I return some results. So let's actually run this function, or actually use it for this data example. So with the high school and college GPA data set, read in the data, estimate the model. Next, I'm going to run the function. Examine.mod.simple, first argument, this is where I got the results from the LM function. I do want to do the constant error variance test, and I also want to do the box-Cox transformation calculations. Put the results into an object called save.it for the lack of a better name. Now, at the very beginning of the very end of class, when we ran this, if you notice that there's this plus sign that's indicated right here, this is asking me to add something to my plot. Specifically, in the lower right-hand plot only, I can click on particular points that identify the observation numbers. So I'm simply left-clicking on it. To exit out of this, of being able to do this, I right-click, stop, and then the rest of the plots are created. Let's take a look at save.it. If I do names, save.it, you see information of what's stored inside of there. So for example, if I type save.it, $Levine, that should look familiar from what we saw earlier today. If I did save.it, $lambda hat, I get that lambda hat value from the box-Cox transformation. Let's take a look at the plots more closely. First of all, the first set of plots are simple box and dot plots for the predictive variable and the response variable. Remember, all we're doing here is looking for, let's say, odd things in our data. Maybe we have a data entry error, for example. And from taking a look at this, it seems like everything's okay. What would be an example of something that would concern me? Let's say that the response variable had values greater than 4.0. Well, if the response variable is called GPA, you can't have GPAs that high, so that would indicate to me there was probably a data entry error. Okay, the second set of plots are shown here. Let me actually come over here to Word so I can make this a little bit bigger. And also I can write on it. Okay, so simply, upper left-hand corner plot, response versus predictor variable. Okay, that's simple. Next plot, residuals versus predictor variable. What am I looking for in this particular plot? Excuse me? Yeah, patterns. And if I do see particular patterns, what does that say is a problem with my model? Linearity. So I have a problem with x. X is not specified correctly in the model. What do you think here? Yeah, it looks okay. So let's move on. Residuals versus the estimated mean response. In other words, y hat. What am I looking for in this plot? Patterns. This helps me look at for constant error variance. Do you see any problems? Okay. Now note that these plots look very similar. Why does that happen? Because of linearity, exactly. Remember, y hat is just a simple linear function of x, or I should say it the other way. X is a simple linear function. I said it right. Y hat is a simple linear function of x. So why are we looking at two different plots to do that? Why are we looking at two plots that are basically the same? It all comes down to when we start adding additional predictor variables in our model, starting in Chapter 6, then we won't be able to have this equivalence there anymore. So, the book at this stage says, okay, well, let's get you used to you looking at two different plots, because you will always have to later when you have more than one predictor variable in the model. Okay, semi-studentized residuals versus y hat. What does this plot tell us? Do I have outliers? Okay. Doesn't look like I have any. Nothing's beyond -3 and +3. Now, notice that I pointed out particular observations there by just, again, simply left-clicking on them. I only did this here just to demonstrate that this could be done. Typically, the only time that you would ever want to actually identify an observation is if you had one, let's say, that was down here, or if you had one that was up there. In other words, outside the borderline. That helps you figure out, well, where's my potential outlier? Now, the last set of plots are shown next. Residuals versus observation number. This is typically only meaningful if we had, let's say, time as a predictor variable. Histogram of the semi-studentized residuals. What are we looking for here? Normality. What do you think? Yeah, it's not looking the best, but you got to be careful always. Take into account the number of observations you have. Also take into account the number of bars that are being drawn. We have 20 observations only, and we basically have places for 6 bars there. It's going to be typically hard to judge normality on such a small sample size. Normal QQ plot. Again, we're looking for the points if they are on the line. It looks like we have some deviations there. But again, we only have 20 observations. As I suggested last time, actually simulate some data that comes from a normal distribution, do one of these plots. And you're likely to find some plots that make you think, wait a second, there's a problem with normality. But since you have a low sample size, it's kind of different.
Is there some sort of formal test, like for the constant variance test?
There is a formal test. I usually don't teach in this class. I believe it's called the Shapiro-Wilks test. That test is often too powerful, meaning that if you have small deviations from normality, it will tell you that it is, but in a practical sense, those small deviations are not very meaningful, so that's why I typically don't do it, just rely on these plots. Okay. Yes?
You realize that we use more observation, we get its problem. What is the quantity of observations can be useful for this model, for these equations? Because it's obvious you have problem with
it's tough. It's a question that statisticians often get asked, and that is, what sample size do I need in order to detect, well, in this case, normality? Well, if you had 1 million observations, do you think it would work? Do you think?
That is make simulation.
Excuse me?
You have to make some simulation with the original observation to increase the sample.
Are you talking about simulation?
Yeah, before.
I guess I don't understand what you mean by...
But you have 5 observations, but in the middle of the observation you have more points. You have to make simulation to increase your quantity.
Well, I mean, you can't just simply increase your data.
Yeah.
Well, you can't do that. My point that I was trying to get across is that obviously 1 million observations is probably going to, you get a good idea of normality is at least approximately to be true. How about 1,000? Probably. How about 100? Yeah. How about 50? Well, not as good as 100. Maybe have a general sense. And, I cannot tell you one particular sample size that's the critical limit that you need in order to judge normality.
Yeah.
Instead, you're going to have to make some judgments on what you see on this plot. We're looking for, when you have, think of it this way, the smaller your sample size, the more deviation you need of the points from the line to make a judgment. And again, if you actually, and I would like you to do this, actually simulate some data on your own and do a plot like this, and you'll see what I'm talking about with respect to, sample sizes and judging different, the points different from the lines. I will tell you this, though, is that typically where you see deviations in a plot like this are towards the ends. And what does that correspond to on a distribution, on a probability distribution? If you were to plot a probability distribution, what would that correspond to? The tails. Okay. Now, why does that happen? Well, let me draw a little normal distribution. Well, that's supposed to be normal. If you were to simulate some data, where would you end up having less data? On the tails. So if I have less data there, less observations there, I have less information there in order to make a judgment. So if I see little deviations, I'm not typically as concerned as if I had large deviations on the ends. Okay. Let's see here. So,
There are ways to correct for the non-normal.
yeah, I mean, we discussed them last time. You could try some kind of transformation. And if that doesn't work, you might have to use a more complicated model, which will be talked about in a more, like a generalized linear model that will be discussed, like 971, 875, and so on. Okay. Now on page 69, 70, and 71, what I have here listed is basically the discussion that we just went through in terms of looking at the plots and making judgments about, do we have a problem or not. Whenever you look at these kinds of plots, this is the format that I want you to follow. Where, for example, let's say number 3 on page 70, constant error variance. I examine the plot of the residuals versus y hat. The points appear to be randomly scattered in the plot. Constant variance test, which we showed you the Levine's test, had large p-values. Therefore, there does not appear to be a transformation needed. That's the type of answer that I'm expecting from you. Rather than the following kind of answer. No problem. Okay?
I want to know what number is larger. P-value is more than alpha, more than what? Probability?
Okay. That's something I didn't discuss. What are we using for a type 1 error rate? Okay. Now, typically in your first stat course, you're always given that type 1 error rate. Alpha equal 0.05. If it's 0.04999999, great. You reject HO. Your research works, or your research hypothesis works. But if it's 0.050001, oh shoot, I can't graduate. I didn't reject HO. I'm screwed. I prefer not to actually state particular alpha levels or type 1 error rates. Rather, think about what a p-value means. What a p-value means is, given that HO is true, what kind of evidence do I have against it? If I have a small p-value that says that it's very unlikely for HO to be true. If I have a large p-value, well, maybe HO is true. Often the example that I give in a Stat 801 class is I talk about the weather. And let's say that the person on the news, before he came to school, the weather forecaster said there was a 50% chance of rain. Would you bring your umbrella to school with you? Oh, you're taking a risk. At least I would take my umbrella to school. So I know there's 50% shot. It may rain or it may not. It's kind of like saying don't reject HO. But let's say the weather forecaster said that there was a 25% chance. Would you take your umbrella? Well, I'm a conservative person. I'd still probably would. Well, let's say the weather forecaster said there was a 5% chance. Would you take your umbrella? Well, probably, it's very, very unlikely that it's going to rain. So I'm going to not take my umbrella. In other words, reject HO. That's the kinds of judgments that you need to make in order to decide, do I have evidence to reject or not reject HO? That same thought process. And so, I'm not going to tell you a particular limit, an alpha level, to do that. Now, often on projects and tests, I will give a particular alpha limit because it's a lot easier for me to grade if we have that. But at least, if you had an alpha of, let's say, 0.05 and a p-value of, let's say, 0.051, I sure hope that you would say, well, my p-value was kind of close, so maybe instead of saying, yes, definitely I have strong evidence against the null hypothesis, you would say, well, there's moderate evidence. That was probably a longer explanation than what you wanted, but hopefully that answers your question. But any other comments or questions? Just the whole idea of p-values and alpha levels, I think it gets sometimes overblown. Okay. Well, what we see here, based upon these plots, is that maybe perhaps we have a problem with the normality aspect. It doesn't hurt to check some transformations to see if you have improvements. So we learned about, for example, the log transformation. So I'm going to do the log transformation. So notice how I do this. I simply say log of college.gpa, and that's the only change that I make. I put the results into sum.fit2, and now I use my examine.mod.simple function again. Let me blow this up a little bit. So, because I made that change, I could have caused a problem with some other aspect of my model. So not only do I have to check my histograms and my QQ plot, I also have to basically go through the whole process again in terms of look at the semi-studentized residuals, look for constant error variance problem, and so on. So based upon what you see on the plots, let's see, they are located on page 372, and I can't get everything on the same screen here. What do you think? Do we have any problems with our model? Looks like no new problems popped up, so that's good. What do you think about normality? Maybe a little bit better. At least the QQ plot looks a little bit better. Not perfect, but it looks a little bit better. And again, histograms sometimes, especially if you have small sample sizes, can be even harder to detect problems with normality. And it all has to do with the fact that I could change what this plot looks like by just changing the class widths on the histogram. So instead of looking at class widths of 0.5, I could change it to maybe 0.25 or 0.75 and get a different look to my plot. And when you have small sample sizes, that can cause big differences. I'm sorry.
Basically, when you reduce the B, you get more noise.
Yeah, yeah. So if I, make the bin or the class size bigger, it's going to be less noisy, and you'll perhaps now be able to see that mound shape that you would hope to have in one of these plots. So I can also do a square root transformation as well. And here's the output. No new problems pop up. What do you think about normality? Yeah, it doesn't look as good as the log did. And I did a inverse transformation as well. No new problems pop up. QQ plots not too bad, although I do have some stuff, kind of far out here. But again, got to be careful with looking at the tails. So, some comments then. Of all the transformations, at least in my opinion, I think the log transformation looks best. And so, that might be an alternative type of model to consider here. Work with the log transformation instead of just the y itself. One thing I want to emphasize, though, is that even if you have some deviations from normality, the methods that we're talking about here are often referred to as robust to these deviations, meaning that everything, generally speaking, will still work out as you would expect, even if you have some small deviations from normality. So because of that, I might not necessarily be as maybe too concerned about the plots that we were seeing for when we just had y itself. Because it's tough to judge about normality with a small sample size, and also I know that I do have some robustness in our statistical method here against normality. So if I were to choose then the log transformation, this is what my model will look like. You can just kind of verify that on your own from looking at the output. And of course, if I wanted to get this back in the scale of just y itself, I would use y hat is equal to e raised to the 0.1518 plus 0.289x power. Okay, so I think either model would work. The log transformation model or the model that had no transformation at all. Both are justifiable. But what about, maybe you also had some access to an additional predictor variable. Let's say, we discussed this briefly, like ACT score. Well, what you could do is now plot the residuals from your original model versus ACT score. And if you see a pattern there, that suggests that maybe ACT score will be helpful. Now, so in other words, maybe I have something like this. So the residuals from the original model that only had high school GPA in it, let's say that you have something that looks like this, or let's say ACT score. Now, why would a pattern in the residuals, plotted versus this other predictor variable, tell you that indeed this additional predictor variable will be helpful to include in the model?
Because the residuals are basically unexplained variability on that.
Exactly. So the residuals are the stuff that's left over from, let's say, just using high school GPA itself to predict college GPA. And if I see some kind of pattern of the residuals versus ACT score, it's like doing a new scatter plot, where I've taken out the effect of high school GPA, and I'm plotting y essentially, after I remove that effect of high school GPA, I'm plotting y versus ACT score, and if I see a pattern there, like a linear pattern, perhaps a linear relationship exists between ACT score and college GPA. That's why one looks at that. Well, we do have an additional variable that we could examine further. Remember that pizza variable that we had previously? Well, what we could do is look at that pizza variable and plot that versus residuals. And this is what I get. Random scattering points. Looks like still pizza is not going to help you do good in college, even after you account for high school GPA. And this matches some similar results that we had before. Lastly now, so what kind of patterns do you look for in a residual versus an additional predictor variable plot? Well, page 113 of the book gives you some other examples, but I do want to bring up one particular one that might be a little bit difficult to maybe understand at first. And that is, consider this high school and college GPA data set again. And let's say I had an additional predictor variable that denoted were you involved in sports in high school? So let's let X could be, let's say, yes if you were involved in sports, or it could be no if you were not involved in sports. Now we need to transform this. In order to consider this in terms of a regression model, we would need to transform this to numerical values. So what we could do is say x is equal to 1 or x is equal to 0, corresponding to yes or no. And I know I have a little bit of a different example here, but imagine that this is actually 1 and this is actually 0. And the blue points are the residuals. Do you think in this particular case that we have a pattern? Yes. Because notice how the residuals are typically positive for the group 1, or the yes, you did participate, and typically 0, where you didn't participate. I'm sorry, the residuals are typically less than 0 if you did not participate. So you do have a pattern. That suggests now adding an additional variable to your model for sports. Again, starting in Chapter 6, we'll look at in more detail how you would actually add this variable to your model. But the authors of our book at least want to make sure that this is getting you thinking that, you know, regression models typically have more than one variable in it. We start looking at models that have only one predictor variable because it's easier. It's easier to first introduce the concept of regression. Okay. Any questions? So that's the end of Chapter 3. You have enough background now to complete this project. I strongly recommend that you get a very, very good start on it before our next class on Tuesday. And then if you have questions, that's a time that you can ask the questions in during class. Again, the project is due Wednesday at noon. And the reason why I'm putting in that due date is because I want to have a chance to grade it and give it back to you, and also to give you a chance to ask questions about, you know, if you didn't understand something on the project before our test. If there's no questions, then we are done for today.